Hello everybody, and welcome to what is likely the final ME 296 lecture for the fall semester in 2020. Just to keep your heads in the game and keep your mind on mechatronics, this is just going to be a little overview of radio control and how that works in conjunction with our circuits knowledge. We're going to go through amplitude modulation and then frequency modulation, including some real simple principles of it, and then examples of some common demodulation circuits. So, amplitude modulation. What is it? It's a method of transmitting information from one place to another. And it does this by varying the amplitude of a carrier signal, where the carrier signal is a constant frequency broadcast that we're changing the strength of or the amplitude of. Carrier signal is a common terminology. This is also used in frequency modulation coming up later. So carrier signal can be thought of as the base, the standard signal. In an amplitude modulation, we change the strength of that signal. And there are several methods for translating that signal. I'm not going to go into how to produce it. That can be done in several ways. The oldest ways involve using capacitors. But we're just going to go through how to decode it. And our method is going to be an envelope detector. So here's what the envelope detector is seeing. It's seeing a constant carrier frequency with an amplitude that is modulated over time, which has a max and a minimum amplitude. And then we care about the wave envelope, which is if you took a sketch of just the outline of all the peaks of our carrier wave, you'd have another wave produced from it with a lower frequency. So the wave envelope is just defined by the shape of the amplitude of the carrier wave if we were to connect all the dots at the peaks of our carrier wave. So now we have our wave envelope. And our wave envelope contains all the information that we care about, and we need to separate it from our carrier frequency, which we only care about in terms of the wave envelope. So we're going to need a wave demodulator to set this up, to get our information out that we want. And here we have an example of a very simple envelope detector. You have an input signal in orange, Vs, that goes to the input, gets bounced around a bit, and then comes out on the green, or VO. And VO should ideally just be the envelope wave, and the characteristics of the carrier frequency should be gone. In an ideal world, all we would have left at VO is our wave envelope. So here we have a little plot over time of our input signal. The blue wave is our carrier frequency. The red line is our wave envelope, or a representation of our amplitude over time. And then the little brown lines represent the actual charge on the capacitor, which is important because remember the capacitor and the resistor are in parallel with each other, and we're taking our output across both of those. So if we have a voltage across the capacitor, that is equivalent to our output voltage. So we need to know what's going on the capacitor. And remember that capacitors take time to charge and discharge based on their time constant. So let's say that we have our input signal at a peak and it hits our wave demodulator, our envelope detector. The capacitor is going to start charging. So it's going to start charging, and hopefully it can charge fast enough that it gets up to where the peak of our blue wave is before the blue wave starts to go down. In between peaks on our carrier wave, our capacitor is going to be discharging, but hopefully slowly enough that it maintains a relatively high charge. If it depletes too fast, we're going to have a situation where our output signal is just the carrier frequency again. And on the other hand, when we have a decreasing envelope, we also need our capacitor to be able to discharge fast enough to keep up with the reduction in our envelope signal. Otherwise, you get something called clipping. So there are some capacitor limitations. And the first one is that our RC time constant must be small compared to the carrier period, or 1 over F carrier. It's got to be small because we need to have it be charging relatively quick compared to when the peaks hit. But the RC time constant must also be small compared to the envelope derivative, its maximum derivative specifically. Because if our envelope is changing very, very quickly, we also need our capacitor charge to change quickly. So RC time constant must be fast enough to keep up with peaks coming in for the carrier, and also fast enough to discharge when our envelope wave is decreasing rapidly. Okay? And now for frequency modulation. The amplitude is constant in this one. Previously we had it so our carrier frequency, we were changing the strength of our signal. And now we are not doing that. Now we're changing our frequency. And this can lead to some really complicated behavior when it comes to how we detect the signal and some interesting side effects when it comes to how much data we can carry, which is why FM is more popular these days than AM. But we're going to ignore almost all that and just keep it real simple. It's also, because of the complicated behaviors, more complicated to decode, but because of the increase in information, it's more often than not worth it to put the effort into decoding it. So we're going to do a little schematic of frequency modulation. And it's going to involve the distance from our default frequency. So if our frequency is increasing from our default frequency, that's going to change our input signal. And if it's decreasing relative to our default frequency, that's also going to change our input signal. And it looks something like this. We have our green line, which is the default frequency, our carrier frequency, and then we have blue, what we're actually sending out with information in it. And then red is what we would ideally get out of it when we decode it. So you see that when the blue has a lower frequency, our red information has a dip, and when it's increasing in frequency in blue, our red has an increase. And that's basically the idea behind that. The change in frequency results in a change in our information signal, both up and down. So frequency deviation results in input signal change. And this can be decoded in many, many ways. And you can have it such that it only gets increases, only gets decreases in our information signal. Lots of different things to do. It depends on what circuit you're using to decode it. And the circuit we're going to look at is the Foster-Seeley discriminator. So this one is a somewhat complicated circuit, but the basic point is you have two frequency filters that when you're at your default carrier frequency, they are equal to each other, and so when you take output across both of them, they cancel each other out. And then when you change away from your default carrier frequency, one begins to overpower the other. You get a positive number or a negative number, and then if your carrier frequency is going the other way, you get the inverse effect. The other one becomes positive and the first one becomes negative. So our input signal is passed through a transformer or an RF choke of some kind, or just something to make it cleaned up a little bit. The two filters are opposed and balanced when the frequency is carrier frequency. And one side effect of the Foster-Seeley discriminator is that these can also detect amplitude changes, which require an amplifier to remove. most of the time, because we only care about the frequency change, not the amplitude change. That's part of the reason why we need a transformer or an RF choke or something like that most of the time. Okay? All right, well, that was just a real brief thing, hopefully to keep you engaged a little bit with mechatronics. Don't forget finals are coming up, and study hard. Thank you.